Welcome dear students. In this lecture I am discussing about the magnetic circuits and their types. This is just a refreshment of what we have studied in our classes. You know that magnetic circuit classified into two types: series magnetic circuits and parallel magnetic circuits. We have already studied the derivation of series and parallel magnetic circuits, yes, but in order to, and also completed the problems of series magnetic circuit, but I think we may be forgotten. Just to refresh this, the derivations, I am doing this video. This is the representation of a simple magnetic circuit, that is an iron core with n number of turns wound over it. A coil having n number of turns wound over it. This is the coil and this is your iron core. Let L be the length of this iron core. In order to make this iron magnetized, you have to pass a current through the coil. Okay, so I be the current passing through the coil. You can represent this as equivalent electrical circuit like this, where this F, that is the MMF. MMF is given as n number of turns into current through the coil. This is the force required to set up the magnetic flux in the iron core. What is MMF? MMF is the force required to set up the magnetic flux or field intensity in the iron core, and that is given by N into I. So this can be represented as a source F. Then due to this magnetic MMF, what happened? It will be flux linkage in the inner iron core, that is given as phi, and this flux is opposed by a parameter known as reluctance. So we can draw the equivalent electrical analogy as E is the EMF instead of MMF, I is the current instead of flux, R is the resistance instead of reluctance. Reluctance is normally represented by S. Here is the notation, a Greek R. So consider this as your notation S. Next we can see series magnetic circuit. So series magnetic circuit may be in two form. One is in rectangular form. Question may be asked in rectangular form or in a circular form. Okay. So in case of a rectangular form, this is the series circuit, means there will be two reluctance path. What is a series electrical circuit? That is two resistance in series. Here there will be two reluctance in series. So this is the iron core and we are making a small cut in this iron core in order to provide this as air gap. So there will be two material, one is iron path and another one is the air gap path. Let N be the number of turns and I be the current through the coil. So there will be flux linkage. Due to this flux linkage, what happened? There will be this flux is opposed by two reluctance path. One is reluctance of air gap and the other one is reluctance of iron gap. I think I have derived the derivation for reluctance, so I am not going with that. So just take the note and find the derivation how you are getting this reluctance. I am writing that equation only. So reluctance is L by mu A. L is length, mu permeability, A is area. So resistance is rho L by A. Similarly, reluctance is L by mu A. L and A is same, but mu, here mu, in resistance it is rho. So take the parameters corresponding to your iron core. So LC, mu C, AC. Corresponding to air gap, take the parameters corresponding to air gap. LG, mu G means air gap, it is permeability, mu R is 1. So mu 0 into Ag. Next, what is the equation for flux? We know that as per Ohm's law, E equal to I into R. Similarly here, MMF F equal to phi into R. What is S or R? That is the total reluctance. So F equal to phi into RC plus RG. So from this equation we can derive the equation for MMF as two equations. First one equation is, so one equation for MMF is F equal to N, number of turns, into I, current passing through the coil. Or another equation is H, magnetic field intensity, into length of the coil, iron core, and The third one is flux density phi. So phi phi into S. S is the reluctance. So this is the important equation you have to remember for studying or for doing the problems in series magnetic circuit. F equal to Na equal to HL equal to phi S. Okay, and flux density can be found out by dividing flux by corresponding area. Next we can see in a ring circuit what will be the flux density or total MMF in a series ring magnetic circuit. Here total reluctance will be, there will be 4 paths, L1, L2, L3 and L gap, LG. So total reluctance will be S1 plus S2 plus S3 plus SG. What is S1? L by mu 0 mu r A1, L2 by mu 0 mu r A2, S3 L3 by mu 0 mu r A3, and SG is mu 0 mu rg into AG. Here mu rg is 1. For air gap it is 1. And total MMF is phi 1 S1 plus phi 2 S2 plus phi 3 S3 plus phi g SG. And what is phi? Flux is flux density into area. B into A is phi g. So it will be substitute in this equation B into area. What happened? Here L by mu 0 mu r, in the denominator there will be an A. In the numerator B into area. So these two A get cancelled and we will be getting this equation. We have already derived, that is why I am not deriving it. Just do it. Total MMF equal to H1L1 plus H2L2 plus H3L3 plus HGLG. This is about the series magnetic circuit. Next we can see about the parallel magnetic circuit. This is the representation of a parallel magnetic circuit. In this there will be three paths actually. First one is path where you are applying the MMF, and second is this path, third one this path, and this path is the central limb, right limb and left limb. Okay, we can see this circuit with the necessary parameters. So you are applying an MMF in the central limb. So MMF is obtained at as N into I. So this is your corresponding EMF or MMF F equal to N into I. And there are mainly 3 parts, 1, 2, 3 limbs. The central limb, let R S or SC be the reluctance, that is AD. This is divided into certain portion B, A, F, E, D, C. It is divided into 3 sections, AD, then A, B, C, D, then A, F, E, D. Let length L be the length of AD, S be the reluctance of AD, and L1 and phi be the flux of AD. Phi, only phi. Phi is divided into 2 portions, phi 1 and phi 2. Let phi 1 be the flux in limb 1, and A1 be the area, L1 be the length, and S1 be the reluctance. And in limb 2, it will be phi 2, area A2, flux phi 2, length L2. Okay. So this can be represented as equivalent resistive circuit with MMF as E or F, reluctance of central limb. Since there is no air gap, only reluctance of the end core can be considered. R1 reluctance of first limb, R2 reluctance of second limb. Then what is the total flux? Flux is total MMF by reluctance. We have already studied that EMF current equal to EMF by resistance. In the similar way, flux equal to MMF by reluctance. So what is MMF? Flux into total reluctance of the circuit. So how will you find the EMF equation or MMF equation of this limb? So consider this as a electric circuit. So how will you apply the Kirchhoff law? E equal to I into R plus I1 into R1. This is the EMF of this limb, and here E equal to I2 R2 plus I into R. In this similar way you can find the MMF of this equation. This MMF N into I equal to phi 1 into S1. S1 is reluctance, phi 1 is flux. And here what is the reluctance of this path or MMF? phi into SC. Okay, so this is the for path A, B, C, D, A. This is one closed path. Either you can take this path or you can take this path. The first path, the MMF equation is Ni equal to phi into SC plus phi 1 into S1. And in the second path, MMF equation equal to this path. Ni equal to phi into SC plus phi 2 into S2. So this is the equation. And in the outer, if you are taking the outer path, what will be the flux? Phi 1 into S1 plus phi 2 into S2 equal to 0. That is phi 1 S1 equal to phi 2 S2. So from this equation you can equate what is phi 1 S1 equal to phi 2 S2. S is as usual length by mu A. S2 length by mu A2. But I have to take the corresponding value of area and mu. Next, this is the case when a parallel magnetic circuit having an air gap. So there is nothing to do with this. We have to consider the air gap reluctance also. So if you draw the equivalent circuit, this is the MMF Ni, and there will be two reluctance corresponding to, this is the reluctance of air gap, this one is the reluctance of air gap, this one is reluctance of ion path. Here also two reluctance of air gap and reluctance of ion path. Here only one reluctance of ion path only. So in this way you can solve this problem. Thank you.